classes was like reactivity of your n-pi star chemistry. We covered three major reactions. One is your cleavage reaction, another is your hydrogen abstractions, and like last two classes we were discussing about addition to pi system. Okay. So, today class what we will do is that to cover the fourth, that is your energy transfer reaction and electron transfer reactions. Right. So, we will start understanding something about your energy transfer reactions of n-pi star reactivity. So, the first thing of energy transfer reaction, it is not basically a photochemical reaction, okay. It is basically a photophysical process, okay. It is a typical photophysical process. So, what happens is that let us consider like two molecules in a system, okay. One we call as a donor molecule, we can call it as G, and then we will have another molecule which we will call as an acceptor. I am talking donor and acceptor with respect to energy. One can be a donor which can donate the energy, okay. Another will be a acceptor. So, what happens is that basically if I take my donor, okay, I am not restricting right now to the carbonyl, okay. I am just taking a donor molecule, and then if I shine light, okay, it goes to its singlet, that is what we studied. Then if it has a chance, it undergoes an intersystem crossing and gives you my triplet. See, I am not so I have a system in which I have both donor as well as acceptor. I am just exciting my donor, I am not doing anything with my acceptor. So, my donor gets excited to singlet, undergoes an intersystem crossing to triplet. Now, this triplet donor collides, okay, basically it collides with your acceptor, and you get a sort of energy transfer where your donor gives this excited triplet energy to your acceptor. Now, your so this collision is between your triplet excited state of your donor and the ground state of your acceptor. After the reaction, it becomes a ground state donor and an excited state acceptor. See, basically I have not shined any light on my acceptor molecule, just I have shined light on my donor molecule. Donor goes to the triplet state and then transfer its energy to the acceptor molecule, fine. So, this process we call as energy transfer reaction. Now, we will see how this happens, okay. You can call as mechanism, or how it happens is you can call as mechanism of this one. So, as I said, I have a donor which gets excited to my singlet, then it goes to my triplet. Now, if I say in triplet my donor electrons should be looking like this, right, because it is triplet state. So, the electron looks like in this state. Now, I have my acceptor molecule, the acceptor is in the ground state, okay. So, it should be mostly singlet. Now, these two come and collide with each other. So, what happens? A type of spin exchange, okay, you can call as an electron exchange or a spin exchange. Basically, a spin exchange happens between your donor and acceptor. So, there will be an exchange of spin. So, if I write, then your donor will be like this. So, you get a proper spin exchange. You can see that donor was initially triplet and acceptor was ground state singlet. Now, there was an exchange in spin where your donor becomes a singlet, which is in ground state, and your acceptor becomes a triplet. So, this process, this is a type of spin exchange process, or it happens because of your electronic exchange. That is how this mechanism works, energy transfer reaction. So, it is so what are the two important criteria, not criteria, what are the two important stages it happens is, one, it should happen from the triplet. Okay. The second thing is that there should be a spin exchange. Okay. The mechanism deals with like this. So, you should be basically from the triplet and there should be a spin exchange. Then you can see the energy of your donor is been transferred to your acceptor, right, without exciting your acceptor. We will see how the application, what is the beneficial use of knowing why to do the energy transfer reactions. Fine. So, this is the proper mechanism of this. Now, we will see like what are the criterias for a donor to transfer his energy to acceptor. You cannot take any donor on any acceptor, which can so that you excite a donor, it will transfer its energy to acceptor. No, there are some criteria which donor and acceptor should take care, so that the energy transfers from donor to acceptor. So, we will just see what are that criteria. So, I will just deal with my first criteria, that is what I said is that I have my donor which is in my excited state, right. Then I have my acceptor. See, these two molecules, okay, has to come together, they have to come here together, then they have to collide. What you think another process can happen when they are two nearby? Okay. One is that they can collide, another, before collision can anything happen if two molecule comes near together. Okay. So, one they can come close and collide, another, most of the time what is a competitive reaction happens in any bimolecular reaction? They can easily diffuse. See, they like to, they can collide or they can diffuse, right. Clear, because that is the process which happens in bimolecular reaction. When two radicals or anything comes together, they always have a competition reactions of diffusing away from each other, right. So, instead of collision, they can also diffuse. So, if the rate of diffusion is greater than your rate of collision, okay, then there is no energy transfer, right. If the rate constant of your energy transfer, rate of the energy transfer is greater than your diffusion, then you will be seeing your energy transfer reaction. That is the first most criteria. So, if they can collide, then you can see the energy transfer. So, what is the first foremost, we can say that if the rate constant, if I say K, okay, KET should be all the time greater than your K diffusion. Now, this should be your first criteria to be, otherwise they will just diffuse away from each other, they will not collide and there will be no energy transfer reaction. Any idea what is the rate constant of your diffusion? Normally any reaction if you do, what is the rate constant for diffusion? How fast it is? Because most of the reaction has been controlled by your diffusion, because molecule try to diffuse from each other. So, the energy transfer is 10 to the power of 9 to 10 to the power of 10 mole per second inverse kT most of the time. If you want the numbers, then they are approximately 10 to the power of 9 to 10 to the power of 10 mole per second, mole inverse per second. So your diffusion should be what number your diffusion you think? Just study 10 to the power of minus 14 mole per mole inverse per second. We have studied a lot, na? So most of the reaction, what happens most of the time, it tries to diffuse very fast because it's a very dominating process. Okay, if you overcome that process, then you are seeing reactions and everything happen. Okay, so if my energy transfer is faster than diffusion, then there will be proper energy transfer reaction happening. That's your first criteria. Okay, now we will see the second one. The another important thing is I have my donor, okay, energy, and I have my this is the excited energy of my donor. Okay. There are two options acceptor can be. One, my acceptor can be energy like this, A star, or my energy of my acceptor can be like this also, right. I have one acceptor molecule, I have a second acceptor molecule. So, which will be good to transfer the energy? I am going from D to D star. Okay. The first case will be good because it will be a downhill process. It can happen. This will be a type of an uphill which you do not want thermodynamically, right. So, what it says? It says that energy of my donor should be greater than the energy of my acceptor. Right. So, these are the two important criteria basically for energy transfer reactions to happen. Okay. One, your energy transfer should be greater than your diffusion. Second is that the energy of your donor should be greater than your energy of acceptor. If this two condition is satisfied, most of the time you can see energy is transferred from your donor molecule to acceptor molecule. Clear? Okay. Now, what we will do? So, what is the great application of this, where we can use this chemistry? Okay. For example, I am taking a benzophenone, or you can take any ketone. Okay, just for namesake I am taking benzophenone. You will take any ketone. If I photolyze this, I get a product, I call it as A. Okay. So, I take any ketone, I get a product, I call it as A or B, whatever. You can get any number of products. Then I am asking you a question, whether this product A is actually coming from the singlet excited state, or it is coming from triplet excited state, or this product A is coming from both singlet or triplet. How to find it? Like you are getting a product. So, people normally, if you do photochemistry, the mechanistic point of view is that whether this happens from singlet excited state, or it happens from triplet excited state, or it happens either from singlet or triplet. You have seen many things where you can see reactions happening from both singlet as well as triplet. So, in that case how this energy transfer reactions will be useful. Okay. So, what I do is that I take this benzophenone, I know the energy values of benzophenone, right. So, what is S1 energy value of benzophenone? Any idea? You have studied that? Around? Excited singlet energy of benzophenone 74 kilocalories per mole, okay, and your triplet is 69 kilocalories per mole. So, what happens, your S0 can go to S1, okay. From S1 I can get the product A, fine, or it can undergo an intersystem crossing to give me from triplet A, but right now I do not know, from which state it is going on. So, what I do is that to the same system, if I am taking benzophenone and doing the photolysis, to the benzophenone what I will do, I will add naphthalene. So, you know what energy of naphthalene, you have studied that. So, this is around 190 kilocalories per mole and 60 kilocalories per mole, the T1. Right. So, now what happens if you excite your benzophenone with naphthalene in the system. So, your S0 will go to S1, then it undergoes an intersystem crossing to T1, then what it does from T1? Because the T1 of your naphthalene is the lowest excited state, we see most of the time photochemistry happens from the lowest excited state, and from this it can transfer its energy to naphthalene, okay, because that is what we studied, from the triplet excited state it can transfer. Then naphthalene will do the chemistry, okay, that I will teach you what naphthalene will do when we go for pi star chemistry. So, you will see pi star chemistry from naphthalene. Now, our question was the product is from singlet or triplet. If the product is from triplet, for example, I am taking one assumption saying that the product is from triplet. If I put naphthalene, what do you expect? If benzophenone is giving me a product A from the triplet excited state, for example, I am making an assumption. Now, I am putting a naphthalene in the system. So, what should happen to the product? Yeah, so that the product will not be formed. So, you cannot see the formation of A, because your chemistry should happen from triplet, but now triplet what it does, instead of forming A, it will transfer all its energy to naphthalene. That means, basically you are quenching your triplet excited state. So, from that I can say yes, my reaction is coming from, my product A is forming from triplet excited state. If my product is unaffected, if it is not unaffected, still I am getting the same product, that means it is forming from my singlet excited state, clear. If half of the, if I am getting like yield of 100%, but I am getting only 50% yield, then you can pretty well say that it is coming from both singlet as well as triplet. So, you are quenching now triplet, so still you are getting some chemistry from singlet. So, that is why, that is how you can know using this energy transfer chemistry, whether from which state you can think about the product is forming, whether it is forming from triplet or it is forming from singlet or it is forming either from singlet or triplet. Clear? Any doubt? This we can basically we call as quenching process, or you can call this as your quencher or donor acceptor, whatever concept. But this will help us to know, this is one of the important application of energy transfer reaction, from which state you are getting your photochemistry. fine. Now we will go down and see the second application, another important application of energy transfer reaction. I will take a type of butadiene. Okay. Since we are going to study pi star chemistry in next class, so it's better that you get involved into this. It's when I photolyze this, see, you know, most of the time alkenes, the energy gap between your singlet and triplet is huge. So you are most of the time you see chemistry happening from the singlet when you go for your alkenes, pi star chemistry. Okay. When I photolyze this, I get two products. I get a cyclization, this type of product. I will explain you the mechanism in detail in this class, okay, how to form, but just you look for the application of energy transfer. If it is done from triplet, so I get this type of product. Your singlet is basically a type of cyclic addition of 1 unit of butadiene, okay, and in your triplet it is 2 butadienes coming together and giving you this product, fine. Okay. Now I say that, see, I want to make this molecule for any of my synthesis, for I want to make this product and then I want to take use of this product for making natural products or whatever. So I say just I want take a butadiene, photolyze, I want only this product, I do not want this, I want the chemistry to happen only from the triplet, I do not want from singlet. So what you can do? You know that pretty well, if I shine my butadiene, if I shine light on butadiene, it is going to go to singlet only and it is not going to do big intersystem crossing. So, I will get only the products from singlet, but I do not want the product from singlet at all. Okay. So, what we can do? In that case, normally we use a type of sensitizer. Okay. So, for example, like I take butadiene, put benzophenone and do the photolysis. I do the chemistry like this, then I get only these products. Okay, how we get it? See, basically you know the energy of your butadiene. Butadiene is 0. This is 120 kilocalories per mole and this will be 60 kilocalories per mole. 60, 120 and 60 for butadiene, singlet and triplet. Now I take my, what I will do, I know my benzophenone energy. Oh, sorry, I just, okay. This is around 74 kilocalories per mole, 69 kilocalories per mole, right. So, what I am going to do now is that I am not going to, I have a butadiene as well as I have a benzophenone, and you know benzophenone absorbs light greater than 310 nanometer, right, 300 nanometer, and your dyeing system have absorption around 190 to 210. So, I can use a filter where the light can come greater than 310 nanometer, okay. And then I can shine only light on my benzophenone. So, what happens, you know that it goes to S0 to S1, then you know benzophenone undergoes very good intersystem crossing to give my triplet. Now, this triplet can just transfer your energy to butadiene. You know it cannot transfer the energy this way, okay. This is properly ruled out. So, it can transfer. Now, the triplet state of your butadiene is got excited. So, I am not exciting now your singlet, basically I am now your triplet has been excited. So, now I get only the product from the triplet. I can bypass my singlet products. So, this we call as triplet sensitizer. Benzophenone is normally a triplet sensitizer. Okay. This reaction we call as sensitizer reactions. Earlier we have seen a quenching type of reaction. This reaction we call sensitizing reaction. You can sensitize whatever state you want. You can sensitize singlet or you can sensitize your triplet states and get the products from what state you want. Okay. These are very feasible. Then you get only benzophenone. You can remove a benzophenone out of the system and then you get your products. These are the two important applications of your energy transfer reactions. Okay. So, we have seen energy transfer reaction. So, we have seen that energy transfer reaction is nothing but it is a physical process, photophysical process where donor and acceptor comes and collides, and then the donor from the triplet transfers energy to the acceptor. Okay, that is what we studied, and we said that the diffusion, your energy transfer rate should be greater than your diffusion, the energy of your donor should be greater than your energy of an acceptor to take place. Then basically we studied two important applications that you can use quenching study, that means you can know from which state the products are forming. Then if you want you can excite that particular state and get your products. Right. So, that is all about energy transfer reaction. Fine. This you are going to use once you go to pi star chemistry. Most of the time you know pi star chemistry happens from singlet, but if you want triplet products then you have to use your source of benzophenone. You should not take a sensitizer in such a way that it should do its chemistry. Instead of this I can take acetophenone, and you know acetophenone undergoes alpha cleavage. You should not take that type of sensitizer. Sensitizer is something which should just transfer its energy, it should not do its own photochemistry. Then you will be getting the products from that. Fine. So, the next reaction, the last one of n-pi star reactivity is your electron transfer reaction. Okay. We will see that now. This is another class of reaction, but this reaction you have seen doing photo reduction of benzophenone. You have seen these reactions, but in this case instead of any hydrogen abstraction from the solvent, I use like donors type of electron donors. So, I have my same way I can take my benzophenone, I take an amine. When I photolyze in the presence of an, for example, I take an amine like this. Okay. I get your nice benzophenone. This you have studied this reaction, but not in the presence of an amine, but you have studied in the presence of isopropanol. like different solvents, you can get nice benzophene alcohol. But in this case the reaction is little bit different. Okay. So, we will try to understand the mechanism, then you will know how far it is. I cannot cover in one page, so I will take the next page. We will do the mechanism of this. I have benzophenone. You know that all the steps, because now you are familiar with this. So, now we have a step like this. Okay. We have studied in the model of alkoxy radical, what alkoxy radical can does in a model example. We said that an alkoxy radical, if it has an amine type of system, it can abstract a non-bonded electron from a nitrogen, then we call that reaction as redox type of reaction, right. We have studied, I just showed in the model compound of an alkoxy radical in the earlier class. So, same way your O dot can abstract, okay, electron from your nitrogen atom to give me minus plus. Okay. This you call as, see, you have seen many reactions where ion pair is forming, right, where you can see, but this is a radical ion pair. These are some peculiar examples where you can see radical ion pair. We call them as a radical ion pair, and it is most like it is in a cage. Okay, it is more like it is in a cage. That is very important on this type of electron transfer chemistry. Once your O dot picks up the nitrogen, you get a radical ion pair, and that radical ion pair is in cage. See, that is why I am saying the diffusion is very important. If these two molecules do not diffuse, for example, they stay like together, then what happens? Then they can do back electron transfer. The electron can return back, giving me the starting material. See, that is very important in this reaction. This is very competitive process for your electron transfer. Whenever you do a forward electron transfer reactions, you always get a back electron transfer. Okay. That means this reaction is, you can make it in the other way around. Okay. That happens always. That is the problem, little bit problem with the electron transfer reaction. You have to find out that in a system where there is no back electron transfer happens. We call it as BET. If it diffuse, for example, instead of doing a back electron transfer, you take a system in such a way that it tries to diffuse from the cage, they come out very fast. Then you end up with a you get a system like this. Okay. This will be also in system. Now, what happens, this can O minus can abstract an hydrogen. Okay. A proton transfer can always happen from here. My O minus can go and abstract this hydrogen, because this is the fissile hydrogen now to apply. If that happens, then I will end up with a system H. dot OH plus I can just shift this electrons to get me a system like this. Fine, because I will get 2 electrons, I will give 1 electron to the nitrogen, make it N double dot with fill this nitrogen electron and keep 1 dot here. So, then you know that this can combine with itself to give me benzphenol, that you can expect, or this two can combine with each other. We can see this type of products also. You can get this type of products also, right? Here it can make a bond. So, that also happens, but this is the major product you get most of the time, benzophenol. So, in electron transfer reaction, you most of the time you should take care that you avoid this competitive back electron transfer, because that will happen most of the time, because they form like a cage radical ion pair. Before diffusing, they try to again do the electron back and then get to the starting material. So, since you know diffusion is very fast, you get things happening to give you a products. Fine. Okay. Now, we will see what is there is any, now this is itself it says that you can reduce now your benzophenone, okay, with systems, or you can form your CC bond formation, all these things. We will see one good application recently has been done using this electron transfer reactions. Okay, you will see that. See one good application. You have studied about protecting groups, right? So, you can take any acids, you can protect your acid, and then you use most of the time acid and base to deprotect them, right. So, I want a system in which I do not want to use acid or base, okay. I want to deprotect. For example, I am taking an amino acid, okay. I am just saying, for example, I take an amino acid, I want to release the amino acid in the cell, where I do not want to do any amine like acid or base wash. So, I want to release just like that. So, what that case we can use your light. So, there are many protecting groups in which you can take an amino acid, okay. You can attach to the protecting group by simple chemistry, then you take to the cell in vitro or in vivo, and then you shine light. Nowadays, you have very good system where you can use even visible light, just shine visible light or UV light, then slowly your amino acid will be released. Okay, that is a very good chemistry which is coming out right now in photochemistry, protection and deprotection. Okay, and people are using it for a lot for biological purposes. And if your protecting group basically is fluorescent, then you can even image the cells like fluoropores. Fine. So, I will tell you one example in electron transfer reaction how we can do that. For example, you take your acetophenone. Yeah, you know, you can do your bromination, alpha bromination, you can know this. This will be my protecting group. Okay, just it is a simple. You take acetophenone, you do a bromination, NBS or whatever bromine, you get your alpha bromine. So, this will be my I call them as photo removal protecting group, or you can call them as protecting group. Okay. Oh, sorry, CS2B. Thanks. So, you get a CS2Br. Now, what I do is that I take this, I can treat with any carboxylic acid I want. Most of the time we use amino acids, okay, but you can use any carboxylic acid you want. you get a nice protection, right? I can protect now. It's a simple protection. See, bromoacetophenone is available, even you doesn't need to make it. Okay, you take bromoacetophenone, take an acid, just stir it in DMF with simple bases, you will get your protection. That goes like 98% yield. Then you take this. Now you say, sir, I want to deprotect it. So it's simple. You take your compound, protected compound, use amines. For example, I am using, you can use any like if you want an amine which can absorb at 410 nanometer, which is greater than the visible, like 410 in the visible region, you can make amines like that. You can get any amine you want, okay, depending upon your wavelength, and then just shine your amine. You can end up with the acid back. So we'll just see how the mechanism works. That will be interesting. So, but just you can photolyze this, you end up with this product. Simple reactions. Okay. Nowadays, for cell imaging and releasing of fluorescent compounds, these are chemistries have been used. See, if you want to study some photophysiological reactions happening inside the cell, you want to know how this cell behaves, then you just inject your sample. Instead of this phenyl, if I take pyrene, okay, then what happens? This whole system will be fluorescent. You know your amino acids are not fluorescent, okay, so you don't know which cell it is going to bind. But if you hook up pyrene, then you know it is fluorescent. Then you can just by fluorescent imaging, you can know which cell it is going to bind. You can just watch them, and once it binds, then you shine your light so that the amino acid is released. Okay, this type of works have been, you can see many papers coming in JACs like that. So we'll just now see the mechanism, how it works. See, in this case, what you can do, see, if you want, you can excite your ketone, but in this case, you can simply excite your amine also. Both are same. You can excite your amine. Here, you can, most of the time, you excite your amine. Amine gets excited. A system like this. Now your carbonyl can abstract an electron from your nitrogen. Okay. So you can get a system like this. Fine. So in the previous case, we were seeing this O minus grabbing an hydrogen from your methyl, right? That's what we saw in previous examples. And then you can make your radical to react. This time you can think about pushing this down. Yeah? Okay, if I push this, I can just move this radical. It's a radical. Okay, the second equation is radical. Then I can push this up. Fine. So if dash get an O minus, yeah, that will be abstracting an hydrogen from the solvent or from the system to give me the amino acid back. And then this radical, okay, can abstract an hydrogen from your methyl, okay, to give you type of acetophenone, yeah, you get your acetophenone back plus you get your an amine, right. If you are doing this reaction in water, then you don't then you think your amine get hydrolyzed. Okay. See, most of this photolysis you do it in water because you want to do it with the system, right, in biological system. I just abstract an hydrogen from here. Okay, it's a dot radical. Okay, so yeah, okay, sorry, right. Then you can hydrolyze this in water to give you, normally you know that you get something systems like NHCS3 that you can get it when you hydrolyze. So this is how the mechanism happens, but we are much more worried about your acids, and you can see the acid is been released with, you can release it in a high yield, high chemical yield, as well as you can release with a good quantum efficiency. Nowadays the recently what happened is that, see, instead of taking your amine, I need any electron donor, that is all my idea is, right, anything which can donate an electron. Do you think any other thing other than your organic molecules, which is now there are several papers in Nature recently on this works. In our department also we are doing, some faculties are doing. So you can take gold nanoparticles, okay, you can take titanium nanoparticles, so you can excite them, okay, and you can take an electron from the gold or you can take an electron from the titanium. Okay. So what happens, your carbonyl goes, abstracts an electron from the titanium, then the whole chemistry happens like this. So just and you know that titanium absorbs in the region of what, 410, 440, 450. Okay. So you are going much more in the visible. So you can do this whole chemistry in laser light. See, if I want to release something in the skin, okay, so just I will take my laser light, I can just show it for 30 microseconds or 10 microseconds, my titanium gets excited, my carbonyl takes the electron and releases my amino acids. So my amine, you can say, sir, amine is toxic, but I can think of nanoparticles which are not toxics, like titanium, gold nanoparticles, there are many nanoparticles which are non toxic. So you just have to add to them and just do it. And nowadays people are doing even inorganic complexes like ruthenium. Ruthenium are well known to absorb light greater than 500 nanometers, ruthenium complex. So you make a ruthenium complex and you know rutheniums are very good for giving an electron. So this guy goes and take an electron and do the chemistry. See, not only in this area, see, if I want to do a Pattano-Bucci reaction, for example, or any alpha cleavage or alpha cleavage reaction, you say that I want to do Norris type 1 reaction or Norris type 2 gamma hydrogen abstraction. Normally what wavelength it goes? We do in ketone, okay, so it is 310 nanometer. So you need a photo apparatus for that. So basically you will say, sir, the main drawback of photochemistry, what you say, sir, I cannot do in synthetic lab because I have to get that photo lamp. Okay. So if you can overcome this, you can easily overcome, because you know that carbonyl can abstract an electron. So put some titanium. Okay. Instead of keeping that in the photo lamp, keep it in your CFL bulb. There are many chemistry has been published in Nature, lot you can get, people do just by CFL bulb. Take your CFL bulb which is available, just keep your RB flask and shine, even it does not need a cover board because it is just your bulb, just you can wrap with the paper and irradiate for half an hour, you do all your chemistries. Your Norris type 1, Norris type 2, Pattano-Bucci, 2+2 additions, all are now coming just by using your CFL bulb. Does not need to do anything by the lamp. You do not need now photo lamps. Okay, that is how the PET chemistry has, the electron transfer chemistry has improved, because I have a donor which can absorb light in the visible region and then can donate an electron. So that is nice, huh? Okay. So that is what all about your electron transfer reactions. You don't what? Yeah, that can also, yeah, you want N dimethyl you want N? Oh, CS3. You want this? Okay, sorry. Oh, your carbon has gone. Okay, fine. That should not be there. So that's good. So that's what we were just trying to understand about your photochemistry of N-pi star reactivity. So we have seen, so as to conclude photochemistry of N-pi star reactivity, I will just generalize you some reaction, just for a short summary for 2 or 3 minutes. We will just summarize. Just to summarize, you have a carbonyl and you have earth, this carbonyl can goes to singlet and then undergoes nice intersystem crossing. That is we seen in carbonyl chemistry. Intersystem crossing is facile to give me a triplet, right. And we have studied based on this. First reaction we were studying was cleavage reactions, then we studied hydrogen abstraction, then we studied addition to pi system, we went to energy transfer, and then we went to electron transfer. So we have studied this 5 set of reactions, right. So cleavage reactions, we were thinking about what we studied in cleavage, remember? Yeah. Yes. So we studied acyclic, right? Cyclic systems, and then acyclic systems having beta hydrogen, right. So we studied this 3 basic system in that. In cyclic, as we studied 4-membered, 5-membered and 6-membered like that, but these are the 3 main groups we studied. One is acyclic carbonyl system, another is cyclic, then we studied acyclic which has an beta hydrogen. In hydrogen abstraction, we dealt mainly with gamma, okay, but we said that apart from gamma hydrogen abstraction, we said that we can also see beta, right, and you can think of delta and so on, okay, the number keep on increasing. So we said that even it is very farther, it can do an hydrogen abstraction. Addition to pi system, we divided basically 2. We said that it should be electron rich alkene, okay, and we did for electron deficient system also. So in the last class we were discussing about energy, in this class we were discussing about energy transfer and electron. Energy transfer, I have shown you how the sensitizer works and your quencher. We studied both the things, how you can sensitize a reaction, how you can quench a type of reactions, and then we studied about electron transfer reaction. So these are the basically N-pi star reactivity we concern, okay. So from next, so that's all about N-pi star reactivity. Next class, we start with pi star chemistry, okay, photochemistry of pi star system. So we end of the class now.